Milling as a process has seen many developments. Over the years, many new methods have emerged, each considered to be state-of-the-art at the time. The computing power of today's machine tools and their controls, in conjunction with appropriate CAM software, are the reasons for a new evolutionary step in the field of machining. That is trochoidal milling, or trochoidal performance cutting, TPC for short. Let's start with the differences between conventional methods and TPC milling. With conventional milling, the milling cutter engages the material with its complete diameter. So the feed rate per tooth, Fz, corresponds to the speed of the milling cutter in the feed direction. Until now, this value was a fixed constant for milling. It was given by the formula Fz equals hm square root of d over AE. Fz consisted of the contact width AE, which also indicates the arc of contact, the diameter d of the milling cutter, and the average chip thickness hm. These values were defined for the material to be machined and the machining process, and remained constant as long as the direction remained unchanged. Assuming also a constant feed rate Fz for the milling cutter. It's entirely different for TPC milling. Here, the value which formerly was constant is continually recalculated by the CAM software or the machine controller. This results in a completely new pattern of movement for the tool. Let's look at this in more detail. AE, the contact width, is now continually recalculated. What was constant is now a variable. Take for instance aluminium, which for best results should be limited to a maximum of 66.4 degrees or 0.3 times D. Because of the variability of AE, we can now revise the formula as follows. So from now on, it's the average chip thickness HM that is constant. Modern CAM systems and controllers now use the constant value of the average chip thickness, that is HM, to calculate and control the optimum milling path, thus ensuring maximum machining efficiency. Let's consider the optimum application ranges for the tools in relation to the engagement angle beta and the ratio AE to D for the respective material. For machining aluminium, the optimum engagement angle lies between 10 degrees and 66.4 degrees, corresponding to an engagement ratio AE to D of 0.008 to 0.3. Other ranges apply to uni, stainless, hard machining and superalloys, for which the optimum range lies between 10 degrees and 40.5 degrees. That corresponds to an engagement ratio of 0.008 to 0.12. To keep the average chip thickness constant as the engagement ratio becomes less, we have to increase VF. The result of this strategy is that high cutting speeds are allowed at full cutting depth, whilst at the same time achieving significantly reduced tool wear. This procedure is achieved by overlaying two opposing movements: straight line and elliptical. This delivers many advantages, such as a limited, constant small arc of contact coupled with very high metal removal rates and very low cutting forces. Machining can be at the full cutting depth from the start, whilst achieving low wear. Trochoidal milling is particularly well suited to difficult-to-machine materials. The greatest benefits are achieved for hard machining and for machining stainless and superalloy materials. You too should be optimizing your production processes with these new Garant TPC tools.
Garant. premium quality by Hoffmann Group.